Every manufactured object in human history requires the destruction of raw materials. To create one thing, you must consume another. Economists define this permanent tension as scarcity. It is the inescapable catalyst for every choice made. Because resources like time, capital, land, and human labor are strictly finite, the economy operates as a completely closed system. Within any closed physical system, allocating resources to build a new asset requires an equal, unavoidable subtraction of resources from somewhere else. Analyzing these choices, we don't look at the value of the new asset we gained. We calculate the exact value of what had to be destroyed to achieve it. Every single economic choice we make is ultimately paid for with the physical loss of the unchosen path. In this microeconomic scenario, a student studies instead of working for 150 BDT an hour. They forfeit 450 BDT, gaming and sleep. A common mistake is assuming the opportunity cost is the aggregate sum of all unchosen paths. Economics defines opportunity cost strictly as the value of the single most valuable alternative that was sacrificed. If taking the job was the student's clear second choice, the opportunity cost of studying is exactly the 450 BDT in lost wages. The lesser options of gaming or sleeping are completely voided from the equation. Isolating the single next best option is what allows us to transition opportunity cost from a vague philosophical feeling into a strictly quantifiable metric. To measure that isolated sacrifice accurately, we have to map it onto a precise mathematical grid and evaluate the cost at the margin. In mathematical economics, we formally refer to this as the marginal rate of transformation. This equation calculates the opportunity cost of producing one additional unit of a given good X inside an economy that only produces two goods. The core of this formula is the absolute value of the derivative, dy over dx. That derivative specifically measures the exact amount of good y that must be subtracted from the total system to free up the resources required for your new unit of x. The derivative, dy over dx, operates as the mathematical engine of choice. It calculates the exact physical extraction required to synthesize progress. We visualize this calculus on a 2D plane using a production possibility frontier. Look at this chart plotting good x against good y, defined by a linear dashed boundary. Any point sitting directly on this line represents perfect productive efficiency. At these coordinates, all finite resources are being fully utilized. To get more of good x, the point must travel along the downward slope, sacrificing good y along the way. Because this boundary is a perfectly straight line, the derivative dy over dx is a constant number at every single coordinate. A linear model like this only exists in a system where resources are perfectly adaptable, meaning labor and machinery are equally efficient at producing both goods. A constant derivative proves that every single new unit of x will always cost the exact same amount of y, but perfect adaptability is incredibly rare. The far more common economic reality is represented by this concave or bowed-out curve. In a concave system, resources are highly specialized. A tractor is great for farming, but terrible for manufacturing microchips. Watch what happens to the math when we begin producing good x at the top left. The tangent line has a gentle, relatively flat slope. The initial cost in good y is small, as you reallocate the least specialized resources first. Now watch the point as we push production further along the x-axis, driving toward the extreme maximum limit of good x. At this edge, the tangent line becomes drastically steep. The cost for a single additional unit is suddenly massive. This steepening geometric behavior is formally defined as the law of increasing opportunity cost. Pushing any system to its extreme limit forces highly specialized resources to do jobs they are completely unsuited for. You end up destroying exponentially larger amounts of good y just to squeeze out a tiny fractional gain in good x. When we replace the abstract variables of x and y with real national budgets, the consequences of this geometry scale up massively. Consider a government that decides to heavily expand its military production. We can relabel our axes to fit the classic macroeconomic model: social infrastructure, often called butter, on the y-axis, versus defense expenditures, or guns, on the x-axis. A nation always operates on a concave boundary because its labor force is highly specialized. An aerospace engineer designing a fighter jet cannot seamlessly switch to designing a functioning hospital. Political promises are strictly bound by these geometric limits. The physical adaptability of a country's resources dictates exactly what the government can actually deliver. If the government pushes military production to the absolute extreme edge of the defense axis, the tangent line goes nearly vertical. To build that final, marginal fighter jet, the state has already exhausted all its military resources. It is now forced to extract specialized civilian engineers, concrete, and steel directly from the infrastructure sector. The math on the curve is brutal. That vertical slope translates to a massive drop on the y-axis, just to secure a tiny fraction of forward movement on the x-axis. The actual price of that final military jet represents a total reallocation of societal resources. The cost manifests as the physical absence of the unbuilt alternative, the literal, calculable number of hospitals extracted from society and left unbuilt. The absolute derivative of the PPF provides a measurement of the physical sacrifices demanded by every choice in the universe.